Good afternoon, good morning, or good evening, wherever you are in the world. Welcome to SPI's technology webinar, dealing with fiber lasers as the enabling technology for e-mobility applications. My name is Jack Gabstill, and I've been in the laser industry now for over 35 years. And I feel that this is a very exciting topic that has a huge scope for laser materials processing. Right. Unfortunately, the scroll down's not working. Oh, there you go. Okay, fine. Right. So to the agenda for today, what I'll try and cover is briefly an introduction to SPI, what fiber lasers are, and why they are important to this industry. Deal briefly about e-mobility and what we think it is and where it's going, and what it's doing for the world in terms of the opportunities for a manufacturing environment and also for the ecosystem. Then we'll talk about the batteries themselves that drive the whole e-mobility initiative, and that starts with battery foil processing. Then we'll deal with some of the welding applications that we see in the manufacture of battery and battery cells, particularly in the terms of what nanosecond welding offers. We'll talk a little bit about oscillation welding, and then move on to e-motor applications, where there are a few good laser applications. Now I'll follow that with a summary. In truth, this is a topic that cannot really be squeezed into an hour, and there are lots of other areas that we will not cover today, but perhaps will be part of future webinars. SPI is a UK-based fiber laser technology company. We've been around for around 20 years. Actually, next year, 2020, will be our 20th anniversary. And we've been making solely fiber lasers here in Southampton, but we also have manufacturing capability up in Rugby. We are focused in R&D on lasers and fiber technology. We have a very lean production, very vertically integrated. We manufacture our own fiber and most of the optical components in our fiber laser engines. We have a global sales presence and support presence, and we are very customer focused, working very closely with a whole range, predominantly with laser OEMs who integrate our laser sources into their machines, but also with end users and customers who have needs, manufacturing needs, where laser technology can provide solutions. We are very focused on applications development, and we have a number of applications laboratories dotted around the world, one in Southampton, one in Shenzhen, in China, in Santa Clara, and even one in Seoul in Korea. So these support all of our customers across Europe, Asia, and the Americas. We get involved in working on customer-specific projects where there are specific requirements that need a bespoke solution. We also do our own application development work and have brought a number of process innovations to the marketplace over the years. And we act as a resource for our customers for processing know-how and laser optics know-how to support manufacturing and industrial solutions. In terms of lasers, there are two basic types of fiber laser that we supply. Those are pulsed fiber lasers, which are nanosecond type pulse products, which currently are available up to 250 watts of average power. These are MOPA type lasers that give us a lot of control in terms of the pulse characteristics, enabling us to vary the pulse duration from as short as 3 nanoseconds up to 2000 nanoseconds or 2 microseconds. That's over 3 orders of magnitude of tunability. And that has a corresponding effect on the peak power available in these pulses and the pulse energy. But at the end of the day, sometimes many of these applications are about the average power that is available. And it's amazing how much a 200 or 250 watt laser can achieve in terms of productivity. Then we have the CW or continuous wave fiber lasers, and these are available from 100 watts all the way up to 10 kilowatts and are more traditionally used for cutting and welding applications and also for additive manufacturing. I suspect that most of the people listening in are very well versed with the versatility of these sources, but also in the benefits that fiber laser technology brings in terms of high productivity and flexibility. They're very efficient compared to conventional or old sources such as lamp pump YAGs and CO2 lasers. So they have a high wall plug efficiency. They also offer users low cost of maintenance. There are very few parts in the laser that need to be maintained. So it is pretty much fit and forget. They also are very small, compact, offering a small footprint compared to older technologies. And as a result, they can provide a very high rate of return on installations and projects where they're involved in high volume manufacturing. So e-mobility, you know, it's the buzzword that is on everyone's lips. It's the mega trend for the next decade. And we all understand this to be automotive, cars. We've seen a whole fleet of electric vehicles or hybrids on the roads, or a growing number of vehicles. But sometimes we forget that this also includes other forms of transport, such as bikes, mopeds, even scooters. And, you know, these are pictures I took in Paris a couple of months, well, 6 months ago, to show that, you know, the streets of our main cities are being flooded with e-bikes, e-scooters, and such. And all of these electrically powered. They need cells, battery packs, and also charging points to enable their use. And that's where the opportunities for laser materials processing come. What's also interesting to see is that, you know, as we look at the different geographies, the adoption of e-mobility varies quite dramatically. And I pulled up this slide from McKinsey that shows how China is leading the charge in terms of EV adoption, and that is battery electric vehicles. We probably think we're doing well in US and Europe with, you know, substantial year-on-year growth, but the adoption in China is very dramatic, and as are the manufacturing capabilities for batteries, battery packs, etc. In terms of vehicles, electric vehicles, the lasers touch many of the key components, such as the battery packs themselves, the charger units, HV batteries, control units, electronic power, transmission units, electric motors. There are lots of places and lots of different processes within each of these sectors where lasers can be the manufacturing method of choice. In terms of the key application areas that we see at SPI, they can be broken down into these key 5 areas. There's battery foil processing, which is pretty much right at the beginning of the process in making the actual cells of the batteries. Then we can connect those batteries with bus bars and battery contacts and connections. And there are a whole host of welding processes associated with that. There's applications in electronics. Then we all have to put these cells and pouches into cans and then seal them. And there's welding opportunities there as well. And that's just on the battery and battery pack side. But we mustn't forget the e-motors, the motors that actually drive these vehicles, because there, are significant opportunities for laser materials processing in their manufacture as well. In terms of the lasers we're talking about, as I said, pulse lasers. These are used in battery foil cutting and slitting, coating ablation, foil drilling, hairpin cleaning, tab welding, electrode welding. So a number of different processes. If we look at CW lasers, they're also involved in similar process, also used for battery foil cutting and slitting, tab welding, hairpin welding, electrode welding, can cup welding, busbar welding, and even the housings themselves. And so there is an overlap of these different technologies. Sometimes it's based on volumes and size of components, but other applications are bespoke to specific lasers. And we'll go into that very shortly. So starting right at the beginning, the whole process starts from a battery foil, and these electrodes make up the actual batteries themselves. The foils, we have typically an anode, which is a copper foil. And basically we have cathodes as well. So we have different materials with different thicknesses. And these are formed into the battery and have a separator layer between them, and typically there's electrolyte. But what you see here is the base material, and then the coating itself, which is basically the active medium in terms of the cathode and a carboniferous containing layer on the anodes themselves. And in the cutting process, it's basically called notching, where we're creating these kind of tabs, where they then roll these, or in some processes roll these or stack these cells together. And so from the strip, we need to cut the edges. Typically, in some instances, it's just the bare metal, but in others, it's the bare metal and the coated areas. And that actually causes a lot of challenges, but also the benefits are there. Conventionally or traditionally, these cutting processes and slitting processes were done mechanically or are being done mechanically. The truth of the matter is laser technology is being adopted in new projects and replacing conventional processing techniques as well. So there's a huge scope for deployment of laser technology for this kind of application. In terms of the processing speeds that can be achieved, typically about 1 meter per second for the cathode and 1.5 meters per second for the anode. And a lot of this is linked to the actual processing equipment. So a lot of this manufacturing technology is based on reel-to-reel processing, where it's decoiled and cut or slit in a production line. What is very important to the industry as a whole is the quality of the cut edge. The cut width is of interest, but not a key feature. However, the heat affected zone has to be minimized, and also any burr height that is achieved on the cut edge. There must be no delamination, it's very important. And also there is a great worry about particles generation from the cutting process because of any risks of short circuit in the batteries and the subsequent manufactured batteries themselves. So there is a lot to think about. But here again, you can see an example of a cut tab, and this is an aluminium foil that actually has a third component, which is a ceramic, which is an optional part that gives isolation from the active area to the actual tab material as well. So in terms of foil cutting, you know, the CW lasers are well used and deployed in industrial applications of this type for cutting both copper and aluminium foils. And you don't really need a lot of power. It's, you know, less than a kilowatt typically to get reasonable cutting speeds. These foils tend to be very thin. The copper is continuously going down. A few years ago, they were talking about 10 micron foils. Last year it was 8. Now they're talking about 6 micron foils. So there's not a lot of material, and it kind of can cut it very, very quickly. So whether it's copper or aluminium, CW lasers offer a very good solution for cutting. The edges of these cuts tend to be remelted, so they're not jagged. But the parameters have to be controlled, the focus conditions, to ensure that there is no balling or defects or burrs generated from these kind of processes. And all of these processes are run using scanner-based technologies and don't involve any cutting gases. So they're basically ablation cutting processes. You can also use pulsed lasers for cutting foils as well. And a 200-watt laser clearly will cut slower than a kilowatt CO2 laser, but the quality of these cut edges is also acceptable from an industrial perspective. And that is both on copper and on aluminium. In actual fact, the copper is actually quite challenging, but the high peak power from the MOPA laser enables us to couple in and get good edge cut quality. And it's interesting to see that in many of these applications, we tend to use very, very high pulse frequencies. So the duty cycle is also very, very high. And that enables us to achieve consistent quality at reasonably high speeds. But more importantly is being able to cut the foils that are actually coated, and it's the coated materials that need to be cut. So in actual fact, the process is about cutting thin bare metal and then moving on to the coated areas where the thickness of the material is considerably higher. And that provides a real challenge, and especially on the aluminium, where there is also occasionally a ceramic interlayer as well. So it's about optimizing the process parameters to be able to cope with all the different materials to give consistently good quality or acceptable quality, both on the bare metal, on the ceramic coated area, and also on the active material coated areas. To some extent, this is all about the intensity of the beam on the actual workpiece. And this is characterized primarily by the spot size, which is impacted mostly by the focusing optic lens. So the shorter the focusing optic, the smaller the spot size, the faster the cutting speed, the smaller the heat affected zone. And here you can actually see the difference in the edge kind of qualities that you can achieve based on different conventional lens options that are available for scanner-based processing. But as you can see here, this is based on a 200-watt EPZ laser that we offer. We can achieve processing speeds that the industry is looking for. So what's interesting, or what's important to note, that cutting a battery foil process is driven by spot size, and that means the power density. And it's essential to achieve high speed and good quality. And really what you need to do is a design of experiments to get the best parameters for a given type of material. All of the materials tend to be bespoke. Every manufacturer has their own secret recipe for the coating, the active materials, and they do process differently. So it is important to optimize the processing conditions for each application. And it actually can get quite complicated because here is an example of some of the conditions that we can achieve with a MOPA laser. So the MOPA laser is optimized, and in this case at waveform 36, which is a 500 nanosecond pulse, which gives the highest pulse energy and peak power at a frequency of 166 kilohertz. What we find at this frequency is that there is quite a high has and not a very good cutting speed using these parameters. However, if we increase the frequency, and the impact that that has on the pulses themselves is to reduce the peak power and the pulse energy. So you have less pulse energy, but you have more of those pulses. So it will still be 200 watts, but just the conditions of the pulses change. You can dramatically affect the heat affected zone and also the cutting speed that can be achieved. And as you can see, for this particular material and this particular waveform, an optimal performance can be achieved at around 350 to 400 kilohertz. So the conclusion here is that the cutting process does not always require the highest peak power or the highest pulse energy to get the best processing results. And again, as I said before, we can change the pulse duration anywhere from 3 nanoseconds up to 2 microseconds. And there is scope, particularly on the aluminium and the copper. You'd have different parameters based on different pulse durations to get the best edge quality and best productivity. Looking more closely here at the cathode, you can actually see an SEM picture of the cut edge and the associated heat affected zone that can actually be quite clearly seen. If we look more closely, we can see the aluminium almost being redeposited. So this is the aluminium coated material, and there is a bit of recoating. And you know, this is something that needs to be minimized, but it is kind of a controlled feature of cutting with lasers of these kind of materials. In terms of the copper material, it looks actually slightly different. You don't see as much heat affected zone, and also there is very little signs of any redeposited material. There's a lot of active work and research in this area to try and optimize the performance of these lasers on these coated materials. And also there are a lot of projects where these lasers are being adopted in larger volume manufacturing installations. And here is the edge-on view. Again, the cathode, you can actually see the aluminium there. And perhaps in the anode, it's more difficult to see the copper. But what you have to remember is that the aluminium is much thicker, is twice as thick as the copper itself. Our most recent product launch is our 250 watt laser that we are now launching. And that will be setting the benchmark for foil cutting. It is got exceptional beam quality at an M squared of less than 1.6, which means that we can ensure the high quality, small spot size and good depth of field for processing of these kind of materials. There are a number of other potential applications. Some of them are in manufacture, some of them are in R&D, and some of them in development, and some of them are of academic interest. One of these applications is foil cleaning, where lasers are being used to remove the active material or the coatings from the foils, with the objective being not to damage the foil material itself. And these nanosecond pulse lasers are very good at this kind of process. They tend to be used in multi-pass processes where sometimes you use bigger pulses to remove the bulk of the material. And as you get close to the foil, you change the parameters of the laser pulses to tune them down to more selectively remove just the carbon-based or active material from the surface. And the final pass can really leave bright metal with very little damage or removal of the actual material. When measuring the thickness of these foils, it's very difficult to see that any material has been removed, but when looking optically and testing them, we can see that we have 100% removal of the coating materials. Here we tend to have to use the high frequency ranges offered by these lasers, particularly in the final pass of the removal. And this is an example where we can show how fast we can remove. So it's less than 2 seconds, and that's basically a 10 millimeter by 20 millimeter square. So we can achieve the quality that the customers require with no penetration into the copper or the metal foil materials. And this is also the case for the aluminium. Again, slightly different conditions are required, but again, similar processing speeds can be achieved. You've got to remember as well that sometimes the coating thicknesses vary between the anode and the cathode, and also the composition of the materials varies quite dramatically. For example, on the cathode material, it's all the active, cobalt, lithium, and those kind of materials. And if you look closely, you can actually just about see the texturing that is being achieved in the aluminium. It's a softer material, lower melting point temperature, so it's kind of difficult to have no impact on the foil itself. But we do not remove any significant amount of the material itself. Then we've got drilling of holes. Again, this is more of academic and R&D interest. We believe it's for improved electrolyte filling. We do see this kind of application in the manufacture of capacitors, so it is something that is interesting. We can also drill lots of holes in foils, and our EPM laser can drill the foils themselves to remove material. The thought behind this from an R&D perspective is to reduce the weight. The batteries themselves, the weight of the foils, the metal foils in a battery can represent 10% of the weight. It's not all needed there, and that's why people are thinning the metallic content by making the foils ever thinner. But there comes a point at where you can get to in terms of the thinness of the foil. And it's interesting that we can drill up to 40,000 100 micron holes in copper foil, which is pretty quick. And it leaves material that is pretty much transparent. We can remove up to 75% of the material. Again, some of these topics we've dealt with previous webinars, and I've got a link here to the drilling webinar where this topic was dealt with. Other applications on battery parts are marking. Again, the nanosecond lasers are being used for that. Battery foil marking is quite challenging. These foils tend to be on a reel-to-reel machine where the material is moving at very, very high speed. And typically we need high powers on prismatic cells, and actually on the cells themselves. We can put other barcodes and data matrices. We need far less power, and it's less of a challenging application. Another application in terms of the batteries themselves is joining all the tabs together. And currently, industrially, this is done using ultrasonic welding techniques. However, this technique is kind of limited to less than 40 foils. Fiber lasers can be used to do this, but it's quite challenging to get the quality of the weld with very little porosity, with little spatter. It's very challenging. One application that is being investigated actively is the use of a hybrid technique where the ultrasonic is being used for pre-bonding and the laser processing is used for the consolidation. And here are two examples on, I think there are 40 foils in each of these samples where we're using a single mode kilowatt laser to consolidate the bond, and also a 200 watt EPZ nanosecond pulse laser where we're doing multiple spots using a spiraling technique. There's also some interest in welding foils, very thin welding, butt welding. And again, we've developed some interesting techniques for joining these very thin foils together using nanosecond pulse lasers. And even in these small, thin foils, dissimilar combinations, we can get quite good tensile strengths. I think this is over about a 25 or I think it's a 30 millimeter length of connection of weld. Moving on, the next application I'd want to talk to is welding. And in particular, we find a lot of interest in microjoining of dissimilar materials. In the formation of batteries, the busbar material is nearly always different to the material of the battery itself or the lid of the battery that we need to weld to. And the challenges here is that we need to make reliable joints to overcome the problems of brittle intermetallics. And we developed a while ago a novel nanosecond-based welding process to do this. And it complements conventional welding technology. The nanosecond process has a number of process variables that control the heat input. So it's about the spatial and temporal interaction, the control of the pulse duration through SPI's pulse tune technology, which controls, as I mentioned previously, the duration of the pulse, the peak power, and the pulse energy. And again, in terms of the processing, the speed and the geometry is relatively important in terms of getting good quality, reliable joints. It's being used in a number of applications, particularly in consumer electronics, where it's replacing adhesives, stakes, rivets, pins, screws, and even brazing and soldering. And these joints are still electrically conductive with good thermal dissipation, but they kind of look a little bit different to conventional welds. And we found that we can actually weld pretty much, or join pretty much any material to any material. And here's just a selection of aluminium, brass, mild steel, copper, and stainless steel. And we've managed to weld or join every single one of those materials over every other one. And all that done with as little as 70 watt laser. The whole point here is about being able to control the heat input. We want to produce strong welds, particularly with no burn through or witness marks. So the deployment currently in consumer electronics is about making sure that there is low heat input, no witness marks, and joining dissimilar materials, controlling the metallurgy such that there are no brittle intermetallics, or brittle intermetallics do not form a line of weakness that could reduce the capability of those welds in service. And here are just some examples of the standard cell where we're welding onto the top surface a nickel-plated copper tab or an aluminium tab. We can weld these either to the top or bottom. And what the important thing is, when we remove the tab, it pulls off, it leaves the studs, so it breaks in the parent material. And what we can see here is that there is no witness mark whatsoever on the bottom of this material. So we have very good control of the depth of the heat input. Using this kind of technique, we can look at different types of welding approaches in terms of geometries. And this is an interesting concept where we're looking at making grid patterns. It's very fast and flexible and can be tailored to the material shape or the available contact area that you have. But all of these 4mm squares were made in less than 1 second. Most of these materials are either 150 or 200 micron foils. So this is aluminium that's joined to brass, copper to stainless steel, aluminium to copper, stainless steel to aluminium, stainless steel to copper, and titanium to aluminium. So a whole host of different materials, not necessarily all those that you'll see in battery manufacture, but hopefully it shows the flexibility of the process, the versatility, and the broad range of materials that can be covered. Again, it opens up huge geometrical flexibility, and we can design for purpose. So if we want electrical conductivity, we look at area. We can design for pull strength, for penetration, based on the available space, and also on whether we are conscious of having a witness mark or burn through on the second plate. And one of the things that we can do is weld quite thicker plates to thinner plates, even when the thicker plate is copper, for example. This is an example that's in production where we're making cells or battery packs based on 1865 cells, where we are welding different materials, aluminium and stainless steel, and then nickel and stainless steel. And this is a production application where we were just using 100-watt pulse nanosecond pulse lasers, and in a single pack they were creating more than 100 welds, and even using the same laser to cut out this contact sheet. Perhaps that's not most efficient manufacturing process, but that's what this company chose to do. What's been interesting is that we've managed to move forwards in terms of available power. So when we started the welding process, we started with 70 watts. And for welding these very thin foils, like the 150 micron aluminium foil to one of these battery cells, we don't really need much pulse energy, and we can create a spot in a fraction of a second. What's been interesting is that with the higher power, we can benefit from the heat accumulation from welding quicker, which means that we can weld 6 times faster for a 3 times increase in weld or average power, which equates to a halving of the heat input into each of these particular spot welds. And again, not to dwell on this, we've got a separate webinar that we've held previously. Dr. Mike Poulter has given that on the nanosecond welding processes and the applications that they're being used for. Again, this is a more specific application of pouch type cell applications where the tabs are bent over, and here you can see an array of, I think it's 24 spot welds that have been done in 4 seconds. And again, this is an actual application. And in terms of the development process, we looking at aluminium to aluminium, copper to copper, and aluminium to copper. All of those are possible using the 200 watt EPZ nanosecond type laser with good pull forces, and again, reasonably high speeds. We use these spiraling techniques to create these larger spots, and we can effectively make the spot size as big as you want. Although actually, if you go too big, you end up putting in too much heat. So the technique is to use multiple small spots to get the best productivity, interface area, and control of heat input. Other applications for nanosecond pulse lasers, this is an odd one or an interesting one, is these containers into which the pouches go and are sealed. They're painted afterwards, and this is an example where the surface is being processed or textured using a pulse laser to improve paint adhesion. And again, here we're showing the difference between 2 lasers of similar laser power, but with different beam quality. The EPZ has a beam quality of better than m squared of 1.6, whereas the EPM is somewhere around 5. And because it's a larger spot size, more top hat in terms of the energy distribution, it is more effective at processing large areas. Moving now on to other welding opportunities. Firstly, I'll just look at the differences between conventional and wobble welding. What I'll try and do is focus on wobble welding applications, because conventional welding applications have been around a long time, and people are well versed with the capabilities of that process. Conventional tends to be fixed head using large spots, high average power, lower beam quality lasers, preferably a top hat, which is what is generated from a re-imaged end of a fiber, and the weld shape is determined by the beam. You typically use a shielding gas, and you would use some pulsing to avoid potentially cracking. Oscillation welding, or wobble welding it is sometimes referred to, uses a much smaller spot size with lower power ranges, and uses very high beam qualities, typically single mode, where we can actually shape the weld by using the oscillation parameters to control the relationship between weld depth and weld width. Quite often we do need some shielding gas, but there are some applications where it is not necessary. And we can rapidly move the beam to avoid cracking in crack-sensitive alloys, and also to control the heat input and the amount of melt that is being generated. We have a lot of flexibility in terms of the scanner control cards. The oscillation can vary anything from 1 Hertz to 3 kilohertz. We can go through circular motion, ellipses, figure of 8, infinities, linear oscillation, etc., etc. The opportunities there for making patterns to join these or move the beam around within a small area is almost infinite. But at the end of the day, what we're trying to do is create a very small spot and move it around to widen the weld area that we're generating. Here are some examples of busbar welding, copper. So it's 1.5 millimeter to 1.5 millimeter using a 2 kilowatt laser. What you can see is we can achieve, by using this oscillation technique where we're moving the laser round and round, we can almost achieve a square weld profile with a well-defined bottom section, which is pretty flat. There is a little bit of protuberance there, but it is quite minimal, and we can focus it in pretty much to the depth at which we have the interface or the joint in this particular lap weld. And we can control the melt formation, and as a result, the amount of spatter that is generated. Again, this is another image, actually it's pretty similar, but what you can see here is a very clean weld. Unfortunately, in these kind of events, we can't use video because the transmission is poor, but this is a video that shows the oscillation where it goes round and round. You can watch the spatter. If we get the parameters, the oscillation parameters right in terms of the linear speed, the wobble frequency and the wobble diameter for a particular material combination, we can dramatically reduce the spatter generation. And there's virtually no undercut. It's a flat, very little reinforcement. We can control the geometry of the weld. And again, here you can see how we're getting a 2 millimeter by 2 millimeter almost square profile of the weld. And this is always very good in terms of maximizing the interfacial area for the amount of energy input that you're putting into the weld. Not only on copper, but we can do this with aluminium. And again, here we've got 2 kilowatts, 3 kilowatts, 50 micron, different spot sizes. But again, you can achieve pretty good weld shapes here as well. Perhaps not as square as the copper, but we can extend that if the applications require. Here we've only got a wobble amplitude of a mere 300 microns. We could extend that, but that gives us something in excess of a millimeter in terms of interfacial weld area at half depth. There are some interesting applications where we can weld dissimilar materials, and this is one application we did in our lab where we're looking at joining copper and manganese. where we had different thicknesses of materials. We used the 2 kilowatt single mode using oscillation welding, and we got very, very good control of the heat input to create very nice square welds for this particular application. It is a battery application. I'm not exactly sure what it was for. Again, these kind of connectors, connections in terms of bus bars. This is another odd material, which is tin copper alloy welding. Has a propensity to soot and spatter. This is the result using a 6 kilowatt multi-kilowatt fiber laser, and it's very difficult to get consistent quality. However, if you do this joint using an oscillation technique and a 2 kilowatt laser, the speed difference isn't, well, it's half the speed, but in terms of the cycle time in this particular application, the welding speed didn't have a huge impact. But as you can see, the quality that could be achieved, almost zero spatter, bright welds, very consistent over the whole ring, with a good consistency in depth and interfacial area. This was something that the customer really liked. And if you want to know more about oscillation welding, again, this is another topic where we have already given a detailed technical presentation, and that is available on our website or on YouTube. And again, we can use the same kind of applications for other components. They look a bit like batteries, but these are ultra capacitors. And again, it's the same sort of thing where we're joining coppers and aluminiums together, using these oscillation techniques by careful control of the parameters, the oscillation parameters, the frequency and the amplitude and the linear speed. We can get conditions where we're optimized for minimum spatter and high consistency in terms of the performance, depth of penetration, consistency, and top bead quality. And again, on soft pouch electrode welding, here the requirements, again, it's like the stuff that we looked at, or I showed earlier, using the nanosecond processing, where we were looking at individual spots. Here we're talking about lines of weld, and there's various combinations from nickel copper to nickel copper. Again, all of these welds, we're talking about 35 millimeters, done in about 0.2 of a second, with a 1.5 kilowatt laser operating at less than 1.4 kilowatts on the workpiece. Very high strengths are achieved. There's aluminium to aluminium, aluminium to nickel plated copper. So all of the different combinations that are commonly looked at by battery manufacturers are achievable using these oscillation techniques with single mode lasers. And again, stack, we've come across some applications where this is a bit different to the foiled stacks that we're talking about previously, where some of these materials are a lot thicker. And this is an aluminium example where we've looked at a multi-layer stack. The key to the success of this application is making sure that there is no air gap and these materials are absolutely pressed tight together. If that's the case, they can be readily welded reliably and repeatably using oscillation welding techniques. And again, we can get this very square weld with good interfacial area and high strength. So, when talking about bus bars, perhaps, there's some question about CW versus nanosecond. And this is an example of where we're welding packs of cells and using a CW laser. We're welding a 200 micron aluminium foil onto the cells. 3 welds per cell. This process can be achieved up to 50 cells per second. With the nanosecond laser, here we're talking about 200 or 250 watt laser. We're looking at welding copper to the same cells. Again, 3 welds per cell, but we can achieve something about 10 cells per second or 30 welds per second. And again, it's all about horses for courses. We find that the nanosecond laser welds very well copper into other materials, whereas the CW welds aluminium into other materials a lot better. But, you know, at the end of the day, it is about average power that equals the productivity. And so in some instances, with the nanosecond welding process, to get the productivity, multiple laser sources are sometimes required. Moving on now to e-motor processing, there's a couple of things that are of interest from a laser perspective, and that's basically cleaning of the pins prior to welding and also the welding of the pins themselves. These copper wires are typically coated with an insulator, PI or PEEK material, some lacquers, and some proprietary coatings. There's various wire geometries, multiple orientations. Conventionally, these have been either mechanically stripped using CO2 lasers or other fiber lasers or other disc lasers. The problem with CO2 is residual, getting material getting right down to the copper. And mechanical, well, it's mechanical. There's a lot of dust generated, and there's wear of the brushes that are used. We find that our 200-watt EPZ and EPM lasers are very good lasers for this kind of application, and can get high removal rates, and are actually currently being used in industrial installations in certain geographies. The processing times are very dependent on the materials and the coating thicknesses, so it's difficult to generalize on processing data. Copper hairpin stator hairpins. Again, this is a conventional copper welding application. The application needs to be quite clean. The end user is very, I wouldn't say paranoid, but very concerned about spatter generation. And there are a number of techniques. We've been involved in some smaller components where the 2 kilowatt single mode using an oscillation technique is adequate, where these kind of spots are being generated in under half a second. For some applications, that's not fast enough, and people are using other laser sources at higher powers and using different technologies to control the spatter. But, you know, motors come in all shapes and sizes, and particularly for the smaller ones, we found that the oscillation welding technique can be used. So, in summary, this has been a bit of a dance through some of the applications, and it's kind of chopped and changed and moved from one to the other. It's only skimming the surface in terms of the technical details that are available on all of these applications. But what e-mobility manufacturing offers is complexity. It offers scales, precision, and cost. The complexity is that, you know, some of these materials are difficult to process. The scale is that people are ramping up to mass manufacture these kind of components. The precision is all about the quality that's required for making millions and millions of components, where there is a risk from a safety perspective. So the battery manufacturers themselves are very conscious of the need for high quality and above all cost. The challenges of the industry, as we see people moving towards the adoption or wider adoption of e-mobility, is going to be driven by cost. At the moment, electric vehicles are still more expensive than petrol or diesel-based vehicles, and that needs to change to radically alter the adoption of electric vehicles or battery BEVs. And that's all about the manufacturing cost. The battery represents the most significant cost element. And I think there is a general global target to be able to, well, two things really, to reduce the cost of the battery by half and also increase the capacity of batteries significantly so that the range of vehicles can be increased. So in terms of fiber laser solutions, For many of these applications, we offer the fiber lasers offer power and flexibility. They're compact, modular. They offer very high control in terms of the energy that's deposited into the materials processing application. They are extremely stable and cost-effective, low-maintenance manufacturing solutions. And they are solutions for cutting, welding, drilling, and other things as well. So they are an energy source, and the opportunities and applications are almost limited. I say that a new application for laser technology is being invented every single day, and that's what makes this whole industry and the use of lasers exciting. That's all I have to say. What I would like to do is at this point promote our next webinar, which is going to be on nanosecond pulse fiber lasers for cleaning and surface functionalization, that will be given by Dr. Mike Poulter on February the 19th, again at 3 p.m. Register on our website. Okay, so from my perspective, that's all. Thank you very much for your time and attention. I've got a few minutes. I think there's a few questions that have been submitted. Hang on, let me have a quick look to see what there is. Okay, there's one question about alternative laser sources for foil cutting. Is there a move towards using green or ultra fast? Okay, I think that can be answered in a couple of ways. I've seen some of the results from nanosecond green lasers. The quality may be on par, possibly slightly better. The processing speeds are about the same. But however, the cost of those lasers per watt is significantly higher. And what we're seeing is that the end users and manufacturers are being driven by cost, and as such, that's the driving factor. The lowest cost solution that gives acceptable quality will win. And I think that relates also to the ultra fast lasers. Again, they are significantly more expensive per watt. And so the cost of ownership is also quite much higher compared to nanosecond pulse fiber lasers. Okay, there's also a lot of articles. Sorry, I'm just reading this. There are a lot of articles where green and even blue lasers are being used as the best laser source for welding copper because of the lower reflectivity or higher absorption by copper. Okay, to some extent that's true. And you will see good processing samples generated by these people. What sometimes is a little bit misleading is some of the graphs that the proponents of these lasers put up, where they show the absorption characteristics of copper significantly higher than IR on copper, for example, and even show that these graphs where IR at 1 micron is less than 10% absorption on copper. What they fail to tell you is all of this data is based on room temperature measurements. And as soon as the material gets hot, 1 watt of green pretty much has the same effect as 1 watt of red. It is slightly different, but as long as you can create a keyhole and get up to temperature, the absorption of infrared lasers on copper is actually quite good. And that is actually shown by the ability to weld copper, process copper, cut copper with 1 micron infrared lasers. There are some applications, particularly when joining multiple foil stacks, where I have to admit that for the foil stacks are going up to about 100 sheets now, some of the requirements from some of the battery manufacturers. And the results I have seen from some CW green lasers are much better than can be achieved with IR. So at the end of the day, there is no one technology for every single application. There are other technologies that have their merits in certain applications, and these things need to be looked at case by case. But again, the cost per watt of green energy is significantly higher than IR, and also the running cost and the operational cost of those kind of lasers is again higher. I think I kind of answered this one in the actual presentation. It says, looking at comparison of welding speeds, I showed that CW is so much faster than pulse. Why would people bother with pulse? Well, there are certain applications where highest throughput is not required. If you're making batteries for automotive, for example, where you absolutely need thousands of welds to be done, you know, in the space of a few minutes, yes, there's probably CW lasers are the way to go. But there are certain material combinations, thickness combinations, and limitations in terms of burn through and heat input, where the pulsed lasers do offer an attractive alternative. So again, it's case by case. But like I said, one of the applications is thin materials where the copper is on top and aluminium is on the bottom, and you don't want to have burn through, particularly if it's a thin aluminium layer under the copper. With CW, you have to put so much laser energy into the surface of the copper, the top layer, that sometimes you can go straight through the aluminium below. Okay, I've got one last question, and that was, how do you remove the insulator material from around the wire? And the answer to that is using multiple lasers if the wire cannot be rotated, or you rotate those wires. So there's two solutions that are currently used. I've run out of time. I would like to thank everybody who attended this webinar. I hope that there was something in it for you and that I gave you some food for thought. If you do have any more questions, I know there's a lot more questions. I'll try and answer them over the next few days and get back to the people that have posted them. Thank you very much.